In this video, we'll generate the dataset and the trendline Maclaurin SERIESSUM expansion of the Weibull function. Here we have the alpha, which is equal to data validation over the range from 1 to 3. And set. So values of alpha. We can start from 1. Same thing with beta. Data validation, list of items from 1 to 3. We can also start with 1. And the value of k, so data validation, list of items, that's 0 or 1. Data validation, list of items, 0 or 1. 0 if it is probability density function, 1 if it is cumulative distribution function. Now we can fill in the dataset of the Weibull functions. So array formula, Weibull of the x values, comma, and this will be our alpha, comma, this will be our beta, comma, and 0 because this is the probability density function. And the cumulative distribution function, which is array formula, Weibull of the x values are alpha for the shape and the rate, that's our beta, and 1 because this is the cumulative distribution function. And the Taylor-Maclaurin series. So here we can chart this. Insert chart. And we will use scatter chart. So scatter chart is row as header. And for the series, show the trend lines polynomial to the 6th degree. For the label, use the equation. And for the legend, position at the bottom. And the size, this will be maximum. So here's our trend line and a polynomial to the 6th degree. We'll also clean the vertical axis, the number format, none. And we continue the Taylor-Maclaurin SERIESSUM expansion for both. So here we have the formula, which is x to the power alpha minus 1 times the summation of a times x to the power alpha n plus k all over the quantity alpha raised to the power k minus 1 times beta raised to the power alpha. And our value for a with coefficient is -1 raised to the power n over factorial n times b or beta raised to the power alpha n. And our value for n is from 0 to infinity. 16 is good enough. Next, we continue with the coefficient, which is r from -1 raised to the power n. That's for the numerator. Now the denominator. The denominator has two parts, factorial n and beta to the power alpha n. So factorial of n plus k times the second part, beta to the alpha n. So that's beta raised to the alpha, the quantity alpha times n. And enter. Now we can continue with the series sum. So array formula. The first part is x raised to the power alpha minus 1. So x raised to the power the quantity alpha minus 1 times the summation. That's series sum. So series sum of the x values raised to the power alpha n plus k. Alpha n plus k starts with k, yes, and with the increment of alpha n. So alpha n, where alpha begins with Rn starts from 0, 1, 2, 3, and it's multiplied by alpha. So it will be, the increment will be alpha. And the coefficient, it will be the value of this range, which is 8. All over, that's for the numerator. Now the denominator. The denominator has two parts. First, the alpha raised to the power k minus 1. So alpha raised to the power the quantity k minus 1. That's the first part. Now the second part. Beta to the power alpha. Beta raised to the power alpha. And enter. And we will modify our chart to show the equation. Edit chart. Customize. Series. Point size. Maximum. Trend line. Polynomial to the 6th degree. For the label, use the equation. We'll change the color of the yellow. Change that to green because our data set is green. So change this to green. And the red one, the point size will be none. This will be none. But the line size, the line thickness will be maximum. So here we have the polynomials and a trend line. We'll calculate this polynomial regression coefficient using the Linus matrix. To do that, we complete the Linus matrix starting with the power. This will be transpose 0 to 6. And the elements array formula of the x values raised to the power 0 to 6. And the coefficient. Linus, that's the starting with the probability density function, data y, and data x. These are the polynomial regression coefficients. So, and expansion, Linus. This is be our data y and data x. The Taylor-Maclaurin SERIESSUM expansion. And finally, the cumulative distribution function, Linus. data y, and data x. Enter. Let's compare our chart. So here's our chart. Coefficient of x to the 0, 1, 1, 0. And we can toggle this to 1. So 1, 0, 0. That's 1, 0. This is 0. 10 to the minus 33. 3.96 times 10 to the minus 30. This is also 0. Negative 5.15 times 10 to the minus 33. And coefficient of x, 0.99, negative 0.99, positive 0.999, positive 0.99. Coefficient of x squared, 0.497. Then this is negative 0.4968. 0.4968. And the coefficient of x cubed, 0.16. This is negative, and this is positive, 0.16. Coefficient of x to the fourth, 0.0356. This is positive, negative 0.0356. Coefficient of x to the fifth, minus 4.99 times 10 to the minus 3. 4.99 times 10 to the minus 3. 4.99 times 10 to the minus 3. Coefficient of x to the 6, 3.3 times 10 to the minus 4. 3.3 times 10 to the minus 4. This is negative. Negative 3.3 times 10 to the minus 4. Now we can continue with we change beta to 1.5, 1.6, and we can toggle this and change it to 2. You notice this is the exponential. This is exponential decay, and this is exponential saturation. That's because beta alpha equals 1. That's the shape, exponential form. Now we continue with we go back to 1 and start with 1.5. Now it's no longer exponential. So we can toggle this to 1. This is the cumulative distribution function, which is this. And their values, polynomial regression coefficients, are the same. Toggle this to 0. This is probability density function. Their data sets are the same, approximately the same, because there's an error here. And their polynomial regression coefficients are the same. We can increase this to 2. It doesn't work, so we can go higher and toggle this. You can increase this to 2 and 2.5. Beta is 2.5 and beta is 3. When beta was 1.5, at 1, and there's 1.5, and we can toggle this at 2, and we can toggle this and 3, 2.5, and we toggle this at alpha equals 2, starting from 1. It doesn't show, but we go higher. You have a value, and we can toggle this to 1 and 2. We can toggle this to 0. So this completes the use of the array formula and the data validation and the Weibull functions to generate the polynomial and the trend lines of the two Weibull functions, the probability density function and the cumulative distribution function and the Taylor-Maclaurin series sum of both.